So welcome to the April Colloquium of CQT. It's my great pleasure to introduce today's speaker, Professor Masahito Ueda from the University of Tokyo, perhaps the only university in Asia that NUS has to look up to, according to its own praise. Let me introduce the scientific vita of Masahito. He got his PhD in 1991 at the University of Tokyo, working in quantum optics and mesoscopic physics. He then moved on to take the position as a researcher at NTT Basic Research Labs until 1994, when he joined the University of Hiroshima as an associate professor, a position that he held until 2000. During that time, he spent 1 year as a guest researcher at Urbana-Champaign, working with Anthony Leggett. And at that time, he developed a keen interest in Bose-Einstein condensates and ultra-cold atoms, work on which topics he's very well known for ever since. In 2008, he moved to take a full professorship at the prestigious University of Tokyo, where he has been ever since. His work contains well-known publications on BEC, and especially the excitations, like solitons, vortices, other kinds of topological excitations. They're admirably covered with lots of attention to detail in a very good textbook that he has written, that I can vividly recommend to all students and researchers in the field of ultra-cold atoms. He's the author of numerous publications. He has received prestigious prizes in Japan. He's a very approachable person, a very nice person to talk to about physics and other things. He will be our guest until Friday. I think he's happy to talk to everyone. If you're interested, please come forward and see him later on. Today he's going to talk to us about information, thermodynamics, and fluctuation theorem, a long-standing interest of his since a couple of years. We're very happy to have you here, Ueda-san. Please, the floor is yours.
Thank you very much, Code. So first of all, I'd like to thank Code for the kind invitation. It's my real pleasure and honor to pay a visit to this very famous place. Today, I'm going to talk about information thermodynamics and fluctuation theorem. This work was done by my former students, Takahiro Sagawa, in collaboration with Sound Kim and Simone de Liberato. As we all know, that Maxwell utilizes information to decrease entropy of the systems. So suppose that we have two boxes. On the left-hand side, we have hot molecules. On the right-hand side, we have cold molecules. When we open a door, then the system thermalizes to a uniform temperature. Now consider a tiny intelligent being which can measure, sense, and open and close a door. Then the Maxwell demon can revert this system back to this system. So this is the second law, and this is the reverse second law, which the Maxwell demon is capable of. In modern terms, Maxwell demon is a feedback controller at the level of thermal fluctuations. And here there is a decisive link between information and thermodynamics, because the Maxwell demon can make a measurement of a molecule and use that piece of information to make a feedback control. And Maxwell himself thought that this demon could violate the second law. But he also thought that it might not be relevant practically because the molecules are too small to manipulate. This is what he wrote in his famous book. But now, Maxwell demon is relevant in solid-state qubit, nanomechanical devices, and molecular devices, and even biological macromolecules. In these nanosystems, information processing is carried out at microscopic levels, yet they usually have direct contact with thermal reservoirs. Because here is a superconducting qubit, which is in contact with the substrate at a given reservoir temperature. Therefore, information processing must be compatible with the principle of thermodynamics, in particular with the second law of thermodynamics. So quantum information deals with the fundamental constraint of quantum mechanics on information processing. But now, principle of thermodynamics should have some constraint on information thermodynamics. Which constraint do they have is the main subject of today's talk. And in ultra-cold atomic gases, they have optical lattices with single atom detection and addressing. Then there might be an also interesting question. So the quantum phase transitions such as superfluid multi-insulator transition may be modified due to the back action of the measurement. Because here, they were able to address atoms with single atom resolution. Then if you measure the position of our atoms, then atoms tend to localize. Then the question is does that localization act in favor of multi-insulator transitions? Or something like that. So measurement back action could have some profound influence also on the quantum phase transition. So two main objectives of this talk is that I would like to explain why Maxwell's demon is actually perfectly compatible with the second law. So this is actually not the real issue. The real issue is rather the thermodynamic energy cost of information processing. I will explain why the second law should be trivially met in every stage. And then I will present a new fluctuation theorem that combines entropy production with information gain as a unifying framework of information thermodynamics. So in thermodynamics deals with entropy production, and which need to be related to information gain. How they can be related is the main subject of today's talk. The decisive observation in this context was made by Girard. He mentioned in 1929 the following: the second law is not threatened as much by this entropy decrease as one would think. As soon as we see that entropy decrease resulting from intervention, this is Maxwell's demon, would be compensated completely in any event if the execution of such a measurement by the demon were always accompanied by the production of k log 2 units of entropy. In that case, it would be possible to find a more general entropy law, which applies universally to all measurements. Tellingly, this decisive observation written in blue was made in a subjunctive past. And this is perfectly understandable because it took another 20 years or so before the decisive concept of information entropy was introduced by Claude Shannon in 1948. And also 60 years before the mathematical framework of measurement theory was firmly established, owing to the development of quantum information. So two elements are necessary to address this question. One is the concept of information entropy. The other is how to mathematically characterize the measurement process. Now, as an illustration, let's review Shillard engine as a quintessential model of Maxwell's demon. So suppose that a molecule is enclosed in a box at temperature T. Then we insert a ball in the middle. At this stage, we do not know in which box a molecule is in. Then Maxwell performs a measurement to find out in which box a molecule is in. At this stage, Maxwell's demon gains log 2 knot of information, left or right. And he then can utilize these pieces of information to perform feedback. If he found a molecule is on the left, he does nothing. If he found a molecule on the right, then he just pushes this box to the left without any energy cost. Then, after that, by isothermal and quasi-static expansion, he is able to do kBT log 2 of work to the external world. This is an essential description of Szilard engine. Now here is a thermodynamic balance sheet. By the measurement, he was able to decrease entropy. But decrease of entropy implies increase in free energy. And this increase in free energy can be utilized to perform work to the external world. Now, then how about the consistency of the second law? In the initial stage, the system has log 2 nut of information because we do not know in which box a molecule is. And at this stage, the memory's entropy is 0 because the memory is prepared in the standard state. It's standard 0 state. So entropy is 0. Now, by the measurement, memory's entropy is increased to log 2. But the point is that there is a one-to-one correspondence between the state of the system and the state of the memory. And this correlation is captured by the mutual information, and which is minus log 2. So log 2 plus log 2 minus log 2 is log 2. The entropy is conserved. So no violation of the second law. Now, the daemon utilizes this mutual information or correlation between them to perform a feedback and to bring the system back to the original state. After this feedback, because the system state is back to the original state, so the entropy of the system is 0. When the feedback is perfect, then there is no longer correlation between this and this. So this mutual information is cancelled. But memory remains the same. Therefore, the memory's entropy is log 2. So the entire entropy is still log 2. So now we see that at every stage, here initial stage is log 2, middle stage log 2, and the final stage log 2. So entropy of the system is perfectly conserved. So actually, there's no issue of the second law. Sometimes in literature that one has to erase this entropy, erase this memory to save the second law. But that is not necessary. The key point is that in each stage, the system and memory and correlation combined, then the entire entropy is conserved. And it is not the erasure of the information, but it is the mutual information, correlation between the system and memory that saves the second law. Okay. And this is, in hindsight, is as it should, because the second law has nothing to do with the thermodynamic cycle. But second law has to be satisfied at every stage. Okay. And as we see, at every stage, the second law is satisfied. So this is actually not an issue. The issue is rather the energy cost for example, the measurement and erasure of information. Yes, please.
I want to ask, like, in each step, measurement and feedback, they are perfectly reversible in practice?
That is a practical issue. Here we assume that measurement is perfect and the feedback is perfect.
Perfectly reversible. There is no irreversible.
No irreversible at all. So this is perfectly reversible. It is an idealized situation. And if it is not ideal, then there is some entropy production. Yes. But again, in that case, the entropy is positive. So again, there is no violation of the second law. Okay. So some remarks about mutual information is in order here. So mutual information describes correlation between subsystems, system and memory. And the point is that this makes entropy non-additive. Okay. But becomes negligible in the thermodynamic limit, as in ordinary thermodynamics. This is why in ordinary thermodynamics, the entropy law is additive. But when the system size becomes mesoscopic, then the mutual correlation between the system, one part of the system to the other becomes very important. And that mutual information, non-additive part of the mutual information is very crucial. The most importantly, this mutual information can be used as a resource to reduce the entropy of the system. So when we perform the measurement, then there is some correlation between ourselves and the system, which is established. And also that makes the entropy non-additive, but that is something we utilize to reduce the entropy of the system. Now, the information theory versus a physical law. So information theory, of course, has developed independently of physics. But implementation of information processing must be based on physical law. Therefore, as Landauer famously puts it, information is physical. And therefore, logical irreversibility entails energy dissipation. So this is a famous tenet advocated by Landauer and also Bennett and many others. However, there is a rub here. From my point of view, it is true that implementation of information processing must be based on physical laws. But information entropy and thermodynamic entropy are two different concepts. In fact, there is a great deal of arbitrariness as to how to encode information in physical systems. So this is a point. This is a point. And therefore, logical irreversibility does not necessarily lead to energy dissipation. Only when we encode information entropy in one-to-one correspondence with thermodynamic entropy, then they become equivalent, and the logical reversibility leads to energy dissipation. But that is not necessarily the case. So in particular, the erasure of information can be done with no thermodynamic energy cost, which I will show later. So in connecting information entropy with thermodynamic entropy, our strategy is to treat non-equilibrium dynamics of the system on the heat bath a la Dzerzhinsky. So Dzerzhinsky's contribution is that he showed that one is able to follow the dynamics of non-equilibrium process via the Hamiltonian. And we use this non-equilibrium technique to deal with this process because every information processing is intrinsically non-equilibrium. And we characterize Maxwell's demon in terms of operational quantum measurement theory. So class operators and something like that. So this is a brief description of the formulation. We start with the system and the bath and the interaction between them. And the initial state is assumed to be at thermal equilibrium state. In ultra-cold atomic or AMO community, for example, ion cooling or something like that, this condition is not necessarily needed. Okay. And the initial assumption of thermal equilibrium is needed if we want to relate work to the thermodynamic concept. Okay. And then the entire system gets entangled via the unitary evolution. And then Demon performs quantum measurement on the system described by a set of measurement operator, where K is the outcome. And depending on the outcome of the measurement, Demon performs feedback control on the system via a unitary operator, which depends on the outcome, U sub K. Therefore, in modern terms, Maxwell Demon is characterized by a set of measurement operator and unitary operator. So this is a mathematical characterization of Maxwell's Demon. And eventually the entire system gets thermalized by another unitary operation. Therefore, the initial state and the final states are related according to this formula, where EK is given by entanglement, measurement operator, feedback operator, and thermalization. And this middle two terms, measurement operator and feedback, describes the demon. By the way, in the original setup of Jarzynski, there is no demon, so there are no those two terms. And EK is unitary. So this is a Jarzynski formulation. The only new element here is that we introduce the demon term in between. But precisely because of this non-unitary part, we can reduce the entropy of the system. So if the evolution is unitary, then entropy of the system is conserved. It is because of this non-unitary part we can reduce the entropy of the system. And according to this formula, we can show that the entropy of the von Neumann entropy of the system before initial state and after final state is bounded by above by this quantity, where I is what is called classical quantum mutual information, because this is described by the von Neumann entropy for the system and the Shannon entropy for the outcome. Outcome is always classical, which is Shannon, but the system can be quantum, which is von Neumann. So this mutual information is called classical quantum mutual information, according to those researchers. This upper bound can also be rewritten in terms of this formula, where delta S is a change in von Neumann entropy before and after the measurement. And the chi is a so-called horrible chi, which describes the degree of accessible information about the system. So if the measurement, in the ideal case, if the measurement doesn't disturb the system, then this is zero. Then I is simply given by the horrible chi. Therefore, the upper bound of the entropy reduction. This is the upper bound of the entropy reduction is determined by horrible chi. This means that upper bound is determined by distinguishability of the post-measurement state. And this is quite natural because we can perform feedback on the system, the more distinguishable the system is. So the upper bound is given by the horrible chi is quite natural. Now, the second law, entropy reduction here implies the gain in free energy. And without the demon, the second law is given by this familiar form. The amount of work which can be extracted from the system is bounded from above by the change in free energy. Now, with the demon, as I discussed, this entropy can be decreased by the amount of mutual information. And since minus and minus is plus, therefore the amount of extractable work can be extended by the same amount. The upper bound of the work that can be extracted from the heat bath increase with the assistance of the demon. So this is the first result of this talk. Now, then, since we get an extra work, so the next question is what compensate for this excess work? And there is a long history about this. And Breland says that it's an energy cost for the measurement. And Bennett, by explicitly constructing a model which requires no energy cost for the measurement, he claims that it's an energy cost for information erasure, which compensates for this extra work. According to our view, actually, both of them are correct. So both of them should be described on an equal footing. In some case, this is correct. In some cases, this is correct, because we can also extract an explicit model in which there is no energy cost for the erasure of information. Okay. The minimum energy cost for information gain is given by this. So if we perform the measurement and if we want to gain information I, then the minimum energy cost is given by this. So the more information you want to get, the more work need to be done on the system. So this is, in a sense, quite natural. Other terms are just the second law. In particular, in a thermodynamic system, this is 0, and this information gain has a maximum value which is equal to h, Shannon entropy. So in the ideal case, this is equal to this, and this is 0. So this means that the lower bound for the measurement is 0. There is no fundamental thermodynamic energy cost for the measurement, okay, in agreement with Charles Bennett's discussion. Okay. Then what is the minimum energy cost for the erasure of information? The result is given by this. The second term is a famous Landauer term. H is a Shannon entropy, which is log 2 for 1 bit of information. Therefore, in order to erase 1 bit of information, the erasure cost is kBt log 2. So this is a famous Landauer term. The point is that we should not miss the conventional second law term, okay, delta F, which is a free energy term. And this can compensate with this if we properly construct the memory structure of the system. For example, usually one assumes that memory has an equal volume. In this case, one can show that this term vanishes, and we have a famous Landau formula. But again, the point is that there is a considerable degree of arbitrariness as to how to encode information on physical system. So, if the volume of binary 0 and 1 is t to 1 minus t, volume ratio is t to minus t, then the energy cost for the erasure can be given by this. In particular, if the volume ratio is 4 to 1, then we can show that this term arises from this precisely cancel this Landau term, and the energy cost is 0. So in this case, there is no energy cost for the erasure of information. Okay. The point is that in this case, actually there is an energy cost for the measurement. So in this extreme example, actually the Brilland's argument is correct. Now, the measurement cost is, as I mentioned, given by this. The erasure cost is given by this. The point is that the second law part has a minus opposite sign, and the Landauer term also has a opposite sign. So in total energy cost for the measurement and the total energy cost for the erasure, those two terms cancel. What remains is a mutual information. So we can say that the fundamental energy cost arises not from this term or Landauer term, but from mutual correlation. And this is, in a sense, in hindsight, seems quite natural, because the real action or effect of the measurement is to establish correlation between ourselves and the system, which is characterized by the mutual information, and therefore which should impose the lower bound of the entire energy cost. Yes.
Just a quick question here. For I, here you mean the classical quantum mutual information?
Yes.
Right. Just to clarify. Thank you.
Yeah. Okay. And in the first part, I show that the amount of work which can be extracted from the system is extended by this amount. And the second part, I show that, however, the measurement cost and the erasure cost together cost at least this term, this energy. Therefore, the net energy gain, which is given by this work gain minus measurement cost minus erasure cost, then in this case, this term cancel, and we again recover the conventional second law. Okay. So the system plus the demon as a whole obeys the second law of thermodynamics. However, these individual inequalities serve as a second law of information dynamics, thermodynamics, in which effects of measurement, erasure, and feedback are treated on an equal footing. So as a whole, second law is always okay, of course. But if we look at the details, then those individual inequalities can play some role. Now, let me discuss how to extend Jasinski equality in the presence of information exchange. So without feedback control, Jasinski's equality holds. So Jasinski showed in 1997 that exponential minus beta work minus free energy change, which ensemble averaged gives just 1, regardless of non-equilibrium process, okay, for arbitrary process, provided that initial state is canonical. Now, with feedback, we can show that the left-hand side is the same, but the right-hand side is modified from 1 to gamma, which we call efficacy parameter of feedback control. Then the question is that left-hand side can be measured. The W can be measured, free energy difference can be calculated. So the question is, can we calculate the right-hand side? And of course, the answer should be yes. Okay. Here is how to measure gamma. So for a given control protocol, which I denote Y, we can consider the time reversal protocol. Let's denote that time reversal protocol as lambda dagger, which is just minus t, time reversal of the original protocol. Then we follow the thermodynamic process under this time reversal protocol and measure whether this time reversal process successfully revert to the original state. Then by this measurement, we can calculate the probability of successful reversal. And there are many possibilities for the protocol. So if we sum this probability over many trajectories, then which gives gamma. So gamma measures the efficacy of the feedback control under thermodynamic fluctuations. If the feedback control is perfect, then we can always revert the thermodynamic process back to the original. But if the thermodynamic fluctuation is large enough, then we are not able to efficiently revert the final state back to the original state. So in this sense, gamma measures the thermodynamic reversibility under feedback control. Let me illustrate this with the simplest Shillard engine. So in the Shillard engine, the forward process is we insert a box and measure the location of a particle and perform feedback and quasi-static expansion. Since this is a thermodynamic cycle, free energy difference is 0, but this can perform work by this amount. Therefore, the left-hand side is equal to 2 because W is kBT log 2. So this is equal to 2. The reverse process is this. So we start from this final state. And since in this case the feedback is perfect, so we can follow each process with unit probability because the feedback is perfect. There is no thermodynamic fluctuation which hinders final state from following the forward process. Therefore, for each probability, left-hand side and right-hand side proceeds with unit probability. So the sum of those two is equal to 2. So the efficacy parameter is 2, which is equal to the left-hand side. So this generalized Jasinski equality holds for this ideal case. Fortunately, we have a colleague. Yes, please.
Like for example, if I go to the forward process, the
Yes.
entropy change is 0 if you consider every process to be ideal, every step to be ideal.
Yes. So
And no free energy change, no entropy change. Then
there is entropy change. Between here and here, no free energy change because the systems are the same.
cycling.
But here, the entropy is decreased because initially the volume is 2. In the intermediate stage, volume is 1. So there is some entropy decrease.
And then again, this volume is
Then eventually, by quasi-static expansion, the volume is double. So by this process, we do this amount of work to the external world. And from this stage,
and that work comes from due to entropy increase.
yes, entropy increase.
So first measurement decrease the entropy,
And then some expansion increase entropy.
so total change in entropy is what?
0.
0.
0. Yeah.
Okay, maybe I'm confused.
Yeah, here I get log 2 of entropy by the measurement. Here the entropy increased by the same amount.
Okay, so total entropy change is 0.
0.
And total free energy change is
Again 0.
And then how can that point will be that much? I mean, because when you just put work, entropy, and free energy in equation, then everything is 0.
Well, 0 if we see only initial and final state. But in the intermediate stage, from here to here, this wall expands from here to here. So in this process, we can perform extra work to the external world, which is given by this. Yeah.
But we have to somehow done a work in terms of measurement and feedback, which decreases the entropy, because we have to put a slide in between and then measurement.
Here, yes.
Perform a measurement, and then this
In-
supposed to some work, no?
In this process, the entropy is decreased.
Okay.
Yes.
Maybe continue, please.
Yes. Okay. Fortunately, we have experimental colleagues at our department, and who did experiments to check this generalized Jarzynski equality. So their idea is this: they use Brownian particle on a staircase. Okay. This particle can summary hop up or down according to thermal fluctuation. Since there is a potential drop, so in a natural trend is for this particle to move just down, okay, probabilistically speaking. Now, suppose that a demon monitors location of a particle, and if the demon found that the particle is here, then the demon insert a wall here to prevent this particle from going down. But because of the thermal fluctuation, then this particle has no choice but to move upward according to thermal fluctuation. Now, once the demon found that this particle moves up, then the demon inserts again another wall here to prevent this particle to going down. And this insertion can be done with ideally zero work, extra work cost. But yet, by this act, the demon is able to use thermal fluctuation to move this particle push upward. So this is the basic idea. Experimentally, they prepare nanoscale beads. Okay. A pair of beads, one of the beads is anchored to a glass. And this beads can rotate freely on the clockwise or anti-clockwise. And this bead is a polyethylene, so if one apply electric field properly, then this electric field can act as an effective potential for this dimer particle. And this dimer particle is immersed in the water. So this particle can fluctuate clockwise and anti-clockwise in a random and thermodynamic fluctuating manner. Okay. And if we change the relative phase of electric field between this and this, then they were able to invert this potential into the other potential. So they can switch to these two different types of potential by just monitoring the location of this particle. Now, suppose that if a particle, we start with this potential, and if a particle is found to be located at the valley, then they did nothing. But if this particle happened to be on top of the mountain, then without doing nothing, then this particle will move down. So at this stage, they switch the potential to the other one to hold this particle here. Okay. By this way, they were able to prevent this particle from moving down. But there is, of course, experimentally some delay time epsilon. So if this delay time for this switching becomes too large, then this particle will move down. Okay. Now, so this is a time versus the location of the particle. If the delay time is short enough, then the particle location moves up the potential. But if they wait too long for switching the potential, then the particle moves down the potential. Okay. So by changing the switching time, they were able to switch between downward spiral or upward spiral. And this panel shows the net work gain, free energy difference versus work. And the second law, conventional second law, dictates that this difference should always be negative. But for if the delay time is short enough, then for the first two parts, they does have a net work gain by this feedback process. Okay. Then how to measure the efficacy parameter? So this is a forward process. If the particle is found here, they do nothing. If the particle is found here, they switch after the delay time. The backward process is just the opposite. So for this process, we do actually nothing and wait for the same period of time. And eventually just see whether this final state revert to the original state, north. So we measure this probability. For the switching event, okay, they started from this final state, and then at this moment, they actually switch the potential and see whether the final state is equal to their initial state, which is south. Okay. And for each case, they measure the probability for the successful reversal and sum them up, okay, which gives our efficacy parameter. So this panel shows the results. The circle show the left-hand side. They were able to measure this and this independently. Okay. And the squares shows the gamma obtained by the reverse process. So that is an independent measurement. And they agree within experimental error bars. So the generalized Jarzynski equality was proven. Now, finally, let me discuss a slightly different version of generalized Jarzynski equality. So, the same equality can be written also by this formula, where sigma is an entropy production. So without feedback, then just exponential minus sigma ensemble average equal to 1. But in the presence of feedback or information exchange, we can show that sigma minus delta I is a change in mutual information. Actually, ensemble averaged equal to 1. So when we apply this formula to the system, in which case we get some information from the system, then mutual information can be utilized as a source for reducing the entropy production. Because if we view the whole quantity as an entropy production, then by the act of measurement, the whole entropy production is reduced by this amount. Or from this, by the concavity of exponential function, we get this result. Now, when we apply this formula to the memory, then we can say that if we get this piece of information by the measurement, then entropy production has a lower bound which is not equal to 0, but this one. So this means that additional entropy production must be generated by the action of the measurement. This interestingly coincides with the original Girard conjecture. So the final remarks. The conventional second law of thermodynamics presupposes a clear-cut distinction between controllable and uncontrollable degree of freedom by means of macroscopic operation. What the second law tells us is that what can do and what cannot do by macroscopic operation. If the process increases the entropy, then that is something we can do. If the process decreases the entropy, then that is something we cannot do by macroscopic operation. However, the cutting-edge technology requires us to abandon such a working hypothesis in favor of the distinction between accessible and inaccessible degree of freedom. So it's not macroscopic versus microscopic, but accessible versus inaccessible gives a borderline between what we can do and what we cannot do. And the generalized fluctuation theorem, which combines entropy production and mutual information, provides a unifying framework for such information thermodynamics. And according to our view, Maxwell's demon plays a role of the interface between this accessible and inaccessible degree of freedom, like the demon in Greek mythology. So thank you very much for your kind attention.